Theorem, Complementary Slackness Theorem. Statement: for the optimal feasible solution of the primal and the dual system, first, if the equality occurs in the ith relation of the either system, the corresponding slack and surplus variable xn plus I is positive, then the ith variable wi of its dual is 0, that is wi equals to 0. Second, if the jth variable xj is positive in the either system of the jth dual constraint holds as the strictly equality, that is the corresponding slack and surplus variable wm plus j is 0. Proof: let us first introduce the non-negative slack variable xn plus 1, xn plus 2 and so on, xn plus m in the primal constraints, and the non-negative surplus variables wn plus 1, wn plus 2 and so on, wm plus n in the dual constraints. Then the primal and the dual problem in the explicit form can be written as the primal problem maximum zp equals to c1x plus c2x plus so on plus cn xn equation 1 subject to a11x1 plus a12x2 plus so on plus 1n plus a1nxn plus xn plus 1 equals to b1 a21x1 plus a22x2 plus so on plus a2nxn plus xn plus 2 equals to b2 and so on. am1x1 plus am2x2 plus so on plus amnxn plus xn plus m equals to bm equation 2, and x1 x2 and so on xn plus m is greater than equal to 0. Dual problem minimum zd equals to b1 w1 plus b2 w2 plus so on plus bm wm equation 3 subject to a11 w1 plus a21 w2 plus so on plus a m1 wn minus wm plus 1 equals to c1 a12 w1 plus a22 w2 plus so on plus am2 wm minus a wm plus 2 equals to c2 and so on a1n w1 plus a2n w2 plus so on plus amn wm minus wm plus n equals to cn equation 4, and w1 w2 and so on wm and wm plus 1 wm plus 2 and so on wm plus n is greater than equal to cn. Now the multiplying the equation 2 by the w1 w2 and so on wm respectively and then adding, we get x1 sigma I varies from 1 to m ai1 w1 plus x2 sigma I varies from 1 to m ai2 wi plus so on plus xn sigma I varying from 1 to m ain wi plus xn plus 1 w1 plus xn plus 2 w2 plus so on plus xn plus m wm equals to sigma I varying from 1 to n wi bi equation 5. Subject to subtracting equation 5 from 1, we get c1 minus sigma I varying from 1 to m I1 w1 into x1 plus c2 minus sigma I varying from 1 to m ai to w I x2 into x2 plus so on plus cn minus sigma I varying from 1 to m a I n w I into xn minus w1 xn plus 1 minus w2 xn plus 2 minus so on minus wm xn plus m equals to zp minus sigma I varying from 1 to m wi bi equal equation 6. But from the zd equals to sigma I varying from 1 to m wi bi, therefore the equation 6 becomes c1 minus sigma I varying from 1 to m ai1 wi into x1 plus c2 sigma I varying from 1 to m ai2 wi into x2 plus so on plus cn sigma I varying from 1 to m ain wi into xn minus w1 xn plus 1 minus w2 xn plus 2 and minus so on minus wm xn plus m equals to zp minus zd equation 7. Also from the equation 4 we have minus wm plus j equals to cj minus ai jw1 plus a2 jw2 plus so on plus an jwm for all values of j equals to 1 2 and so on, and or minus wm plus j equals to cj minus sigma I varying from 1 to m ai jwi for all values of j equals to 1 2 and so on, and equation 8. Now using the result 7 and 8 in equation 6 becomes minus wm plus 1 x1 plus wm plus 2 x2 plus so on plus wm plus n xn minus w1 xn plus 1 plus w2 xn plus 2 plus so on plus wm xn plus m equals to zp minus zd equation 9. If the x star equals to x1 star x2 star and so on xn star, and w star equals to w1 star w2 star and so on wm star, the optimum solution to the primal and the dual problems are respectively, then the duality theorem we have zp star equals to zd star equation 10. Thus from these optimum solutions x star plus w star of the primal and the dual problems are corresponding slack and surplus variables are xn plus I star is greater than equal to 0 for I equals to 1 2 and so on m, and wm plus j star is greater than equal to 0 where j equals to 1 2 and so on, and then the equation 9 becomes minus wm plus 1 star x1 star plus wm star x2 star plus 1 plus wm plus n star xn star minus w1 star xn plus 1 star plus so on plus wm star xn plus m star equals to 0 from equation 10. This is equation 11. Since all the variables in equation 11 are restricted to be the non-negative, and so their product terms in the equation 11 are also non-negative, the sum of these positive products in equation 11 will be 0 if each of the terms is separately equal to 0. that is wm plus j star x j star equals to 0 for all values of j equals to 1, 2 and so on, and equation 12, and wi star x n plus I star equals to 0 for all values of I equals to 1, 2 and so on, m equation 13. Now if x n plus I star is greater than 0, then from equation 13 we must have wi star equals to 0. That is, if the slack variable in the ith relation of the primal and the positive, then the ith variable primal is positive, then the ith variable of the dual is 0. Again, if wm plus j is greater than 0, then from equation 12 we must have xj star equals to 0. That is, if the surplus variable in the jth relation of the dual is positive, then the jth relation of the dual is positive, then the jth variable of the dual that is primal is 0. Hence the first part of the theorem is proved. B, if xj star is greater than 0, then from the equation 12 we must have wm plus j star equals to 0. That is, if the jth variable in the primal is positive, then the jth relation in the dual of the dual is strictly an equality of the since wm plus j star equals to 0. Again, if wi star is greater than 0, then from the equation 13 we must have x n plus m star equals to 0. That is, the ith primal constraint is a strictly equality, which proves the second part of the theorem, hence the proof of the theorem.